Assalamu alaikum. Today we'll be starting chapter number 29 of Survey and Jude. This chapter will tell us about magnetism. First, we'll go through introduction and brief history of magnetism, and then we'll move on to article number 29.1. So, let's start with the introduction. In the 5th century BC, Greeks already knew that there are some rocks that attract bits of iron. Those rocks were commonly found in a district called Magnesia. So from here, from as they were commonly found in Magnesia, nowadays we call these things as magnets and their property as magnetism. These rocks contain iron oxide, which are called magnetite. In 1100 AD, Chinese used these needles of magnetites to make compasses, and in 13th century it was discovered that magnetites have two places of maximum attraction, which we call poles. Whenever we will take one pole of magnetite, it will always have two poles in it. So it is not possible to have a magnetite having a singular pole. So whatever piece of magnetite we will choose, it will always have two poles. For the time, let us call these poles as A and B. It was noted that A and B and B, they repel each other, whereas A and B will attract each other. There is a difference between electricity and magnetism. In electricity, we can choose a single charge, either plus or negative, but in case of magnetism, we can never choose a single pole. They always come in pair. So whenever we will talk about magnetism, we will be considering magnetic dipoles. Monopoles are not possible in magnetism. So remember one thing, that isolated magnetic poles does not exist. In 16th century, Gilbert discovered that the earth is really a giant magnet. He experimented with compasses, and he was the first person to map out the magnetic field of the earth. In 18th century, Danish physicist Ørsted discovered that a magnetic needle responds to a current in wire, which linked electricity with magnetism. He conducted that current in the wire produces a magnetic field, and magnetic needle moves in response to the magnetic field in which magnetic field which is produced by the wire. After this discovery, a lot of research was done in this area, and the scientists that contributed to electromagnetic theory or fields are Ampere, Faraday, Henry, Lenz, etc. But the most popular of them is Maxwell, and Maxwell gave us four basic equations in which we can relate electricity with magnetism, and these four equations are the base of electromagnetic theory. So now coming to article 29.1, magnetic field and forces. Suppose we have a current carrying wire. Let the wire be perpendicular to the whiteboard. Suppose that we have a whiteboard, and suppose that this is a whiteboard, and the wire is perpendicular, means that it is going into the whiteboard, and the current goes into the whiteboard, and that is the direction of the current is going into the whiteboard. If a magnetic needle is placed in its vicinity, then what will happen, that when the current is going into the whiteboard, then if I place a magnetite in the vicinity of the conducting wire, I can see that the north pole of the magnetite will point in this direction. If I place the magnetite over here, then it will point in this direction. If I place it over here, it will point in this direction, and so on. In this case, it will point in this direction. So I can draw a circle from originating from the North Pole, and it is going in this direction, that is in the clockwise direction. So the magnetic field will be in the clockwise direction when the conducting wire is going into the plane of the whiteboard, and when it is coming out of the plane of the whiteboard, then the direction of the magnetic field will be anti-clockwise. There are two different ways through which we can explain how the cross represents going into a plane, and how the dot explains coming out of the plane. Suppose that we have an arrow over here, and if you see that the arrowhead, it gives us a dot. If I throw an arrow towards a paper, what will happen if the arrow wants to come out of the paper? The first thing that appears on the paper will be a dot, which will show that now the arrow is coming out of the paper. And if I hold the arrow in my hand, then the cross will be at the will be towards my side, and when I throw the arrow towards the paper, this the cross will represent that now the arrow is going into the plane of the paper. So this is one way of explaining that why I can say that the cross is going into the plane and the dot is coming out of the plane. Another way to see this is by corkscrew rule. Most of you have seen a cork opener where you can have um, um, a spiral sort of a thing with a handle, and the other end pointed. You stick the pointed end of the that opener into the cork, and now when you move that cork opener in the clockwise direction, you are basically fixing that pointed end into the cork. So it is going into the cork, and when you want to pull out this opener, you will move with the handle in the anti-clockwise direction, and the opener will take the cork out of the bottle. So this is another way of showing that when the conducting wire is pointing or the current is going into the plane, the field will be in the clockwise direction, and when uh, the conducting wire or the current is out of the plane, then the field will be in the anti-clockwise direction. So these two things represent this thing. Okay, now again the cross is into the plane and dot is out of the plane. Now, to find the strength of the magnetic field, we will proceed as in case of electricity, we have measured the force on a charge with electric field E, and the formula which we have written to calculate the electric force is F is equal to QE, where E determines the strength of the electric field. So this E determines the strength of the electric field. For magnetic field, why we cannot write this formula for magnetic field? It will be very easy to write FB equals to QB, but we cannot write this formula for magnetic field, because the reason is that in magnetic field, the poles or the charges present, magnetic charges are not in singular form. So when we are able to find a monopole for the magnet, then maybe we can use this formula F is equals to QB. But as long as till day, we have not been able to find a monopole for magnets, so we cannot use this formula for magnetic force. Now consider electric charge Q moving with velocity v, and there is a magnetic field B, because the charges they are moving, and because of the movement of the charge we have magnetic field. Where the electric charge is moving, the force is always perpendicular to uh, the velocity of the charges, or the speed of the charge. The magnitude of the force is proportional to the speed of the particle and also to the charge. The force is proportional to the speed of the particle and to the charges present. And again, F is perpendicular to V. Now we will define magnetic field strength as F is equals to Q into V cross P. This equation is usually known as Lorentz force, and it is a sign sensitive equation. So sign sensitive in the sense that if I have a positive charge, it will affect this equation, and if I have a negative charge, it will be affected. Again, if the velocity it changes its direction, it will affect the force, and if the magnetic field changes its direction, it will affect the magnetic force over here. As I have written is Q into V cross B, this F must have a vectorial sign over it, and if I want to find the magnitude, then I may write F is equals to Q V B sine of theta. So this is how we can find the magnetic force uh, on a current carrying conductor, and this is also known as Lorentz force. So this is a sign sensitive equation. Unit for magnetic field is can be calculated by using equation 1, that is F is equals to Q into V cross B. For force we have Newton, for charge we have Coulomb, for velocity meters per second, and I want to find the unit for B over here. So rearranging the equation, I can write B is equals to Newton into second divided by Coulomb's meter, which is Tesla. Tesla is the SI unit for magnetic field, but Tesla is an extremely strong magnetic field. So in most of the cases we use Gausses, and 1 Gauss is equals to 10 raised to the power minus 4 Tesla, and magnetic field of Earth is half Gauss. So this is a little about the unit of magnetic field. Now we will proceed to right hand rule, and there we have two different types of right hand rule explained over here. In the first case, we will have this picture over here. Suppose you have your right hand placed in such a way that you open your palm, then the fingers, when you have not made a fist out of it, the fingers, they will point in the direction of V, and the palm, it will point in the direction of B. And when you curl the finger of your right hand, this will give us V cross B. So we will have the direction of V cross B by curling the finger, and the thumb will point in the direction of force. So this is one way of knowing the direction of force, velocity, and magnetic field. And in the second rule, again, this is your right hand. The thumb will point in the direction of velocity. The fingers, they will point in the direction of magnetic field, and if you move the palm, it will give us the direction of magnetic force. So if I move my palm in this direction, that is coming out of the plane, and then the fingers, they will point in the direction of B, and thumb in the direction of V. So if you move your palm, suppose in this direction, then what will happen, that if the force stays in this direction, but B now at this point it goes in this direction, and V goes in this direction, and your B is, again, it is coming out of the plane. So these are two different ways through which we may know the direction of force, velocity, and magnetic field. Now, there are few differences between the electric force and the magnetic force. When we consider electric force, it acts along the direction of electric field. But in case of magnetic force, it acts perpendicular to the direction of magnetic field. Second point is electric force acts on the charged particles regardless whether it is moving or is stationary, whereas the magnetic force only acts when the particle is in motion. And the third difference is it does work in displacing the charged particle, whereas the magnetic force does no work when associated to steady field, as F is perpendicular to the displacement. So the work done will be zero when we have theta, because cos of theta is 0. So these are the main differences between the electric force and the magnetic force. Okay, now we'll see an example related to the equation or the Lorentz force we have done. The example says an electron in a television picture tube moves towards the front of the tube with a speed of 8 into 10 raised to the power 6 meters per second along the x-axis. Uh, Figure will be given with part B. Surrounding the neck of the tube are coils of wire that creates a magnetic field of magnitude 0.025 Tesla, directed at an angle of 60 degrees to the x-axis and lying in the xy plane. For part A, we have to calculate the magnetic force on the electron. We have to find the magnitude of the magnetic force. For that, the data given is speed 8 into 10 raised to the power 6 meters per second, magnetic field 0.025 Tesla, theta is 60 degrees, and Q is 1.6 into 10 to the power minus 19 coulombs. So the solution for this problem will be, actually we are interested in knowing FB. So we know the formula, that is FB equals to Q into V cross B, which is VB sine of theta. Putting in the values, and I get the value of FB, which is equals to 2.8 into 10 raised to the power minus 14 newtons. Now in part B, it is said that find a vector expression for the magnetic force on the electron. So we have to find the vector expression for the force. For that, we will write the speed in vectorial form, that is the velocity. As we can see that the velocity of the electron is along the x-axis, so I can write 8 into 10 raised to the power x 6 unit vector I, that is pointing in the x direction. For B, it is making an angle of 60 with x-axis, so I can the B, and then B will have two components, that is cos of theta and sine of theta. So I can write this B as 0.025 cos of 60 unit vector I and 0.025 sine of 60 unit vector j. So after simplifying, I get these values for B. Now I have to find force in vectorial form. So what will be the solution? I'll write this force equals to V cross B into Q, but this Q is now for electrons, so I have to place a negative sign for that, because now I'm not finding the magnitude, I'm finding the vector value over here. So for vectors, these signs are very important. So I have written minus Q, 8 into 10 to the power 6 unit vector I multiplied by B, that is the cross product of B. So I cross I will give me 0 and I cross J will give me unit vector K. So I can write minus q into 8 into 10 to the power 6 into 0.022 unit vector k. That is I cross j gives me k. Now simplifying by putting in the value, I get a vectorial form of force, that is magnetic force, equals to minus 0.2816 into 10 raised to the power minus 13 unit vector k newtons. So this is how we will solve this problem when we are asked to find the vector expression for magnetic force.